In this video lecture, we have to derive our Clausius Mossotti relation, epsilon r minus 1 divided by epsilon r plus 2, which is equal to n alpha by 3 epsilon naught. Here alpha is our molecular polarizability, which is a microscopic property of a dielectric, whereas epsilon r is a dielectric constant of a dielectric material. This is our macroscopic property. To derive this relation, we should be familiar with the concept dielectric. In a dielectric material, electrons are tightly bound with their positive nuclei, resulting in zero electrical conductivity. However, an electric field is applied. The positive and negative charges are displaced slightly in opposite directions, resulting in the production of electric dipoles. These dipoles generate an electric field EP that is opposite to the direction of the applied field E0. Therefore, the resultant field E, which is equal to E0 plus EP, here E is always lesser than E0 because field due to polarization opposes the applied field E0. Now we may coin a term polarization, that is the dipole moment per unit volume is termed as polarization. Actually, polarization is directly proportional to local field. Here local field is nothing but the field experienced by an individual atom or a molecule inside the dielectric. So mathematically, we can write P is proportional to E local. P is proportional to E local. Then P equal to N alpha E local. This is alpha. There is molecular polarizability. This N is molecular density. That is number of molecules per unit volume. Here, the value of E local is E plus P divided by 3 epsilon naught. This is our Lorentz condition. Now we have to find out the polarization vector P. Keep this equation 1. To find the polarization vector P, we should be familiar with the displacement vector D. According to Gauss theorem in electrostatics, according to Gauss theorem, the total electric flux linked with the closed network is 1 by epsilon naught times the charge enclosed by it. Mathematically, we can write E dot ds, which is equal to 1 by epsilon naught into Q. This is our Gauss theorem. According to Gauss divergence theorem, or we may write this Gauss law in electrostatics for simple understanding. Gauss law in electrostatics. If you use our Gauss divergence theorem, this surface integral is changed into volume integral. Del dot E into dV. Mere the conversion factor from surface integral into volume integral, which is equal to 1 by epsilon naught into integral rho dV. This is also volume integral. This charge is expressed in terms of charge density into volume. Now we can write del dot epsilon naught into E, which is equal to rho. Here rho equal to rho free plus rho bound. Here rho bound is volume bound charge density. Suppose the polarization is non-uniform, charges are accumulated inside the dielectric material. So the volume bound charge density is given by the formula minus del dot P. If dive P equal to 0, then rho bound is 0. Rho bound is equal to 0. Here rho bound represents volume bound charge density. And at this stage, sigma B is having value. Sigma B represents surface bound charge. Sigma B is given by the formula P dot n cap. Charges are accumulated on the surface of the dielectric. Suppose del dot P is positive, then rho bound is equal to negative. See this formula, rho bound is equal to minus del dot P. If del dot P is positive, then rho bound is negative. This means that only negative charges are accumulated at that particular region. If dive P is negative, rho bound is equal to minus to minus plus, positive. Only positive charges are accumulated in that particular region. In this way, we may understand this divergence property. Here it is convergence, here divergence. With respect to the positive charge, no need to write all those things for your theoretical understanding. I have explained. Now come to this formula, rho bound is equal to minus del dot P. Suppose the polarization is not uniform, more charges are bound within the dielectric material, it may be positive or negative, that is determined by the value of del dot P. Whether it is positive or negative, rho bound is justified. Now this rho becomes rho free minus del dot P. Here rho bound is minus of del dot P. The free charges are originated from our applied electric field. Now del dot epsilon naught into E, which is equal to rho free minus rho bound, that is minus del dot P. This is minus del dot epsilon naught E plus del dot P, which is equal to rho free. Del dot epsilon naught E plus P, which is equal to rho free. According to Maxwell's field equation, the displacement vector D equal to, according to Maxwell's field equation, dive D, which is equal to rho. This is our Gauss law in electrostatic. This is the first Maxwell's field equation, dive D equal to rho. If you compare these two equations, we may write D, displacement vector equal to epsilon naught E plus P. This is the value of displacement vector. On the basis of SI unit, polarization is directly proportional to E, not E local. E is our resultant field. To remove the proportionality sign, we have to introduce two constants, epsilon naught, chi E, then E. This is our permittivity of free space. This is electric susceptibility. See here, epsilon naught is a universal constant, but this chi E varies for various dielectric material. For the given dielectric material, this is a constant. But for all the dielectric materials, epsilon naught is a constant. So that we have used two constants here. Now, substitute this value of P in our D. D, which is equal to epsilon naught E plus epsilon naught chi E into E. This is equal to epsilon naught 1 plus chi E into E. Now, we have to coin a term epsilon, that is permittivity of the medium. Epsilon, which is equal to epsilon naught into 1 plus chi E. Now, this displacement vector takes the form of D equal to epsilon into E. This is one relation. This is another form of displacement vector. We know the dielectric constant or relative permittivity epsilon r, which is equal to epsilon divided by epsilon naught. This is permittivity of the medium divided by permittivity due to free space. Now, epsilon equal to epsilon naught, epsilon r. Now, we can write D equal to epsilon naught, epsilon r into E. Say, this is equation 2, this is equation 3. From these two equations, we can write epsilon naught, epsilon r into E, which is equal to, from the equations 2 and 3, instead of D, left hand side I have given epsilon naught, epsilon r into E. Right hand side is epsilon naught E plus P. From this we can write P equal to epsilon naught to epsilon r minus 1 into E. See here, bring this epsilon naught E here and take epsilon naught outside. We can write epsilon r minus 1 into E. This is our polarization vector P. Assume that this is equation number 4. Now, come to the equation 1. P equal to n alpha E local. The value of P is epsilon naught epsilon r minus 1 into E. Then E local is E plus P divided by 3 epsilon naught. Now, we have to reduce E local further. E local equal to P plus E plus P by 3 epsilon naught. The value of P is epsilon naught epsilon r minus 1 into E whole divided by 3 epsilon naught. This is equal to E plus epsilon r minus 1 into E divided by 3. This is 3 plus epsilon r into E minus E whole divided by 3. 3 minus E, 2E. Therefore, epsilon r plus 2 into E by 3. This is the value of E local. Now, substitute the value of E local and P in equation 1. Assume that this is equation 5. Now, instead of P, we have to substitute epsilon naught, epsilon r minus 1 into E from equations 4 and 5, 1 becomes, equation 1 becomes. The value of P is epsilon naught into epsilon r minus 1 into E, n into alpha. Then E local is epsilon r plus 2 whole divided by 3 into E. Now, remove E on both sides. We can write epsilon r minus 1 divided by this epsilon r plus 2, which is equal to n alpha divided by 3 epsilon naught. This is our Clausius Mossotti relation. This is equation number 6. Now multiply both sides of equation 6 by m by rho. Epsilon r minus 1 divided by epsilon r plus 2 into m by rho, which is equal to n alpha divided by 3 epsilon naught into m by rho. Here m is our molar mass, rho is our mass density. Now we can coin a term Avogadro number, which is equal to 6.023 into 10 power 23 mole power minus 1. This is Avogadro number. That Avogadro number Na equal to n m divided by rho. Therefore, this relation 7 becomes epsilon r minus 1 divided by epsilon r plus 2 into m by rho, which is equal to n suffix a alpha divided by 3 epsilon naught. This is our molar polar stability equation. Suppose if you replace epsilon r, it is dielectric constant in terms of refractive index. Say this is 8. This relation is modified as n square minus 1 divided by n square plus 2 which is equal to n alpha divided by 3 epsilon naught. Or here also we can write n square minus 1 divided by n square plus 2 m by rho, which is equal to Na alpha divided by 3 epsilon naught. So these are all the different forms of our Clausius Mossotti relation. Thank you.